So now we're ready to talk about heat, and we have the foundation in the last unit talking about the kinetic theory, thermal physics, kinetic theory, and now we're ready to talk about heat. We're looking at the transfer of energy from one object to another, and so if we look at this situation here where you've got some food on a skillet, we've got energy being transferred from the skillet to the food, and then you also have energy being transferred from the flames to the skillet as well. And so all examples of thermal energy transfer there. So heat is the energy that is transferred from one body to another as a result of a difference in temperature. And so you must have a difference in temperature for you to have heat, and heat always goes from a hotter object to a colder object, and we'll look at why that always is. When we talk about heat, it's really a form of energy, and so the unit of heat that we can use, and we'll use actually a different unit more often, but 1 calorie is the amount of heat necessary to raise the temperature of 1 gram by 1 degree Celsius. And so the calorie, that's lowercase c calorie, we have that. The capital C calorie is actually 1,000 lowercase c calories, capital C calories. So that's what you see on your food labels, right? And and so just to so we distinguish that there. And so for 1 kilogram of water to be raised by 1 degree Celsius, that's 1 kilocalorie or 1 capital C calories. So there are different ways that heat can be transferred from one object to another, and James Joule came up with this apparatus to explore that. It's a pretty neat thing. You put the water inside here, which is shown in here. Put the water inside. You have these paddles, and you connect a mass to it, and you measure the height of the mass, and from the where it hits on the ground, and this has a certain amount of potential energy, and then you let it go and let it fall, let it fall, let it fall, bring it up, let it fall, and so on. And what you can do is this paddle is going to be swinging through here and then mixing up the water. And then what you can do is you can say, okay, we had a certain amount of potential energy, and we did this multiple times. We can get the total potential energy that we used, and then we can look at how much the water temperature increased, and then compare the two, and then we can find the mechanical equivalent of heat. And this was really important because what they found, or James Joule found, was that 1 calorie is equal to this many joules, and so he was able to take a look at the transfer of that mechanical energy into thermal energy, and this is the equivalent. And so this is what we'll predominantly use here, is the joule as a unit of heat, how much heat, thermal energy transfer from one object to another that we have. And so we can actually calculate what happens in terms of internal energy with a substance. As the water temperature increases, the total internal energy increases. And remember, the internal energy is the total amount of energy, all the potential, the kinetic energy involved in a substance. And to calculate the internal energy, we need to know the number of molecules, because the more molecules that we have, the more internal energy overall that we're going to have, because we're looking at the total amount, mass in kilograms. And then we can look at the average speed as well, and when we calculate that, we'll end up getting the overall energy. And so if we look on the equation sheet that we have, the kinetic energy, average kinetic energy is 3/2 kT. The average kinetic energy, the molecules, we know that K, Boltzmann's constant, K is the gas constant over Avogadro's constant, and so, or Avogadro's number, same thing. And so we have that, and so the N is the number of molecules, and capital N, And so P equals nRT. K there is Boltzmann's constant. And so what we can do is we can take N as the number of molecules and multiply that by K there. And we'll end up getting the total, total internal energy there. We can place R and the number of moles in there, and then we end up getting NR over NA, and then that is the total number over the number of moles. So therefore that is N, and so placing that in there, we get 3/2 nRT, and this is how we can calculate the internal energy based on how much, what's the temperature of the substance, how many moles do we have, and then we'll have the internal energy, what's the total entire amount of energy in that substance, and we can calculate that out. So what I like to do in this lab is we take a bottle and we'll shake this bottle. We have the water inside, and we shake this for a couple minutes and then measure the change in temperature. And so we know that the thermal energy transfer from the kinetic energy there turning into internal energy. Those water molecules are moving faster. The overall internal energy is increased. All right, so 3/2 nRT is what we can use to figure out the overall internal energy, and we have everything there. The number of moles is N, the gas constant R is here, temperature, and temperature must be in Kelvin, so be careful with that. And yeah, and that's. So when we look at the internal energy, we also have to consider the rotational vibrational kinetic energy as well. And so these molecules can be vibrating and shaking, and so we have to consider that as well as we look at the overall internal energy. So a couple things to keep in mind. The internal energy is the total random kinetic energy plus the total interparticle potential energy of the particles. The temperature, we measure the molecules' average kinetic energy, internal energy, total energy of the molecules, and that's really important to keep these distinguished, right? So temperature, average kinetic energy of the molecules, and then internal energy, total amount. So let's take a look at this for L1. What is the internal energy of 2 moles of nitrogen gas? That's 310 Kelvin. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so here's our gas, 3/2 nRT, and we have our values there. So 7,732.02 joules is the total amount of internal energy in these 2 moles of gas that's contained here. That is at 310 Kelvin. Okay, so nRT, that should remind you of P equals nRT, right? That portion there. And so, if we bring the 3/2 to the other side and we place that in for this, PV equals 2/3 U, and we can multiply both sides by 3/2. And this is important as well. We can get the internal energy from the pressure as well as the volume. So if we know what the pressure is, we know what the volume of the gas is, we can get the internal energy, and this will need to be, you'll need to be able to derive that for the exam. All right, so in this one, we're going to practice our derivation of internal energy in terms of pressure and volume. And so go ahead and pause the clip and give this a try and derive that, and then when you're ready to check, you can hit play to continue. All right, so we have our original equation, and we have K as our Boltzmann's constant. We could place that in for K there, so R over NA, the Avogadro's number. And then N over NA is in moles, so we get 3/2 nRT. From there, we can relate this to the ideal gas law and get it in that form. And so 3/2 or 2/3 U equals nRT. And then we can replace that for pressure times volume and then multiply both sides by 3/2. And there we go there. So the internal energy equals 3/2 PV. Okay, so what is the length of each side of the cube container holding the gas in L1 that had an internal energy of 7,732 joules, assuming the pressure inside was 1,952,470 pascals. And so you can first derive that and then solve that. So go ahead and pause the clip and give that a try, and then when you're ready to check, you can hit play to continue. Okay, so we've got our gas